That the universe is vast and expanding is one of humanity's monumental discoveries. But mysteries remain. Why is the universe so uniform? Its temperature and density similar in all directions. On December 6, 1979, at night, a low-key physicist came to what he called a spectacular realization. The very early universe he envisioned had undergone a period of enormous exponential expansion. Fleetingly brief, it all happened within the first fraction of a second. Alan Guth, the theory's originator, called this extraordinary event inflation, and it would stun cosmology. Personally, cosmic inflation enthralls me. I want to meet the scientists and hear their stories. I'm Robert Lawrence Kuhn, and closer to truth is my opportunity. Cosmic inflation is so powerful, so strange, so magical, that before meeting Alan Guth, I had better understand his theory. So I begin at Tufts University with one of inflation's key developers, the director of the Institute of Cosmology, Alexander Vilenkin.
Inflation actually is the theory of the bang, of the Big Bang. Inflation is extremely fast, accelerated expansion of the universe. And it is driven by a very peculiar form of matter, which is called false vacuum. The most peculiar thing about it is that it is a very dense material. Its cubic centimeter has mass, at least the mass of the moon, and probably much higher. But the most peculiar property of this thing is that it has strong repulsive gravity. And this is what causes the universe expand at staggering rate. And since this force persists, the universe expands faster and faster. So it gets huge in a tiny interval of time. So this false vacuum eventually decays. It is unstable. And its energy turns into a hot fireball of elementary particles and radiation. From that point on, gravity of the particles is normal. It is attractive gravity, but this fireball expands by inertia, basically, because it was expanding so fast to begin with. And the end of inflation and the creation of the fireball is what we call the Big Bang. The expansion of the universe that we see today is just the consequence of this force of this initial explosion.
Inflation describes how the Big Bang came about. It is astonishing. Repulsive gravity causing the universe to expand faster and faster, and a false vacuum decaying into a hot fireball of particles and radiation. What we call the Big Bang is the creation of this fireball at the end of inflation. Inflation is what caused the Big Bang to go bang. I now head across town to MIT to meet Alan Guth, one of my heroes. I'm excited to hear firsthand how one man changed our species' understanding of the origin of the universe. I ask Alan how he came to realize one of the greatest insights of human knowledge, cosmic inflation. Alan, the theory of inflation in cosmology, which you discovered, is one of the greatest achievements in human intellectual history. How did this happen? What does it mean? Take us on your journey.
Okay. First of all, a lot of things happened that led up to this, which is important. I first learned about something called the flatness problem, which is crucial, and the ideas of inflation, from a lecture that I just happened to wander into in the fall of 1978, given at Cornell by Robert Dickey. This flatness problem is the statement that to get the universe to come out right, to look anything like what we see now, if you look back at what things must have been like at 1 second after the Big Bang, the expansion rate has to have been just right, or the mass density has to have been just right, to an accuracy of about 1 part in 10 to the 14. Otherwise, the universe either rapidly recollapses or expands so fast that no galaxies form. This idea struck me very much at the time. I was bowled over by it, but had no idea really what to do about it at the time. I just tucked it away in the back of my mind. Also in the fall of 1978, the other important event that got things rolling was a fellow postdoc of mine at Cornell named Henry Tye came to me one day and asked me about magnetic monopoles and grand unified theories. He had said, well, why don't we try to figure out how many of them would have been made in the Big Bang? At first, this idea sounded crazy, and he really had to twist my arm to get me to work with him on it. When we did, we discovered that the universe would be swamped with magnetic monopoles if one combined standard ideas from grand unified theories with standard cosmology. So that led us to start to scratch our head about whether or not there's any way to modify standard cosmology to make it consistent with grand unified theories and the observed absence of magnetic monopoles in the real universe. We came up with the idea that these magnetic monopoles would be extraordinarily suppressed if in the early universe there was an extreme amount of supercooling, cooling below the temperature of the phase transition without the phase transition yet happening. We assumed that this supercooling would have no effect on the expansion rate of the universe. In our calculations, we just put in the standard expansion rate. And then the real excitement happened one night when I went home and looked at the equations that described how mass densities affect the expansion of the universe, which are all really standard equations of cosmology. And it became immediately apparent that the consequences of this supercooling would result in a form of matter that would really turn gravity on its head and cause it to become repulsive instead of attractive, and that would propel the expansion of the universe and perhaps even explain why the universe was expanding, which is what became the theory of inflation itself. And I realized that same night, it was extraordinarily exciting, that this process of exponential expansion would actually solve this flatness problem. The expansion rate that's driven by this gravitational repulsion is just the right rate to drive the universe to this critical density that the universe needed to have to extraordinary accuracy in the early period.
And in describing that feeling, what did you write in your diary?
Well, it wasn't exactly my diary, but on the page that I was doing the calculations on, I wrote, when I realized that it would solve the flatness problem, spectacular realization, and put a double box around it. And as far as I know, it's the only time I've ever put a double box around anything I was immediately excited about it, but I was also immediately worried that, it was just too simple, too obvious, too wonderful to be true.
So what happened the next day and afterwards?
I roughly did the calculations that night, and then probably slept a little bit, and then woke up excitedly the next morning and bicycled to my place of work, the Stanford Linear Accelerator Center. And I did make a note, and it actually was my diary, that I broke my bicycle speed record that morning. Then I started telling people about it, and some people got very excited. The next important event was really just a few weeks later when I was having lunch in the SLAC cafeteria. People began talking about something which had been mentioned in a recent paper by Tony Z called the horizon problem, the problem of how the universe got to be so uniform, which I had not recognized was even a problem. But it turns out to be very hard to understand how the early universe got to be as uniform as it apparently was. It really doesn't make sense in the context of the standard Big Bang model. But as soon as I heard about it, I realized that inflation would solve that too, because this enormous period of expansion would mean that you'd be taking a very, very tiny region of the early universe and stretching it out, and very, very tiny regions are usually uniform. And then when you stretch them, this process of stretching would maintain that uniformity. I gave my first seminar about this at the end of January of 1980. At SLAC, and that's where the excitement really started. I got a very positive reaction from the audience, and by that spring, inflation really had permeated the US physics community.
And since then, inflation has really come to be a standard part of the theory of how the universe was created, with more and more observational and indeed experimental data that supports it.
That's correct. And so far, the observations are just wonderfully in prediction with, in fact, the simplest versions of inflationary models. So it's been a remarkable success and amazing. I just love it.
Cosmic inflation revolutionized cosmology. The simple elegance of Allen's discovery is breathtaking. In an unimaginably short span of time, all space underwent stupendous exponential expansion. For the age-old mystery of how the universe began, here was the hidden key. Yet the story was not so simple. Because Allen's cosmic inflation, it seemed, would never end, and thus no universe could ever form. Allen's theory was sweeping and startling, but his cosmic inflation did not work. Something was amiss. I go to Princeton to meet the man who figured out how inflation could end and thus could work. Physicist Paul Steinhardt. How does cosmic inflation explain the origin of the universe? I asked Paul.
Up until Einstein's work in the earlier part of this 20th century, the idea was that space is something that we move through, but is itself static, inert. So we can talk about our position in it, how fast we move through it, but the space itself doesn't respond to anything else that's happening. It's a separate entity. After Einstein invented his special theory of relativity, which described the way space and time change according to different observers, space is something which is elastic. It can stretch, it can warp, it can wiggle. So you immediately ran into even a more elementary problem, which is if the universe is expanding going forward in time, what's going to happen going backwards in time? It will have contracted. And eventually it will have contracted to a point where everything we see, all the matter and radiation in space, will have contracted to a point. That means the temperature and density would have become infinite, and space would have, in some sense, disappeared, according to Einstein's theory. This is what we call the Big Bang, or the cosmic singularity. And so it immediately introduced a very uncomfortable idea that space and time have a beginning. And then it led to a second problem, which is, okay, if we imagine that it has a beginning, and this is some violent quantum event, then what comes out of this event should be something turbulent. It should be very non-uniform. It should be hotter in one direction than another. Space itself can be curved and warped. But the universe doesn't look that way at all. The universe looks remarkably uniform, and space seems hardly warped at all. So the moment we had the idea of a beginning, turns out we had to invent a new idea to explain the smoothness that would emerge right after the beginning. So this has forced us logically into, well, the only solution we know if the universe has a beginning is to have a period that we call inflation.
Now, how does that work?
It turns out that hidden in Einstein's general theory of relativity is a possibility for a form of energy which would have a kind of anti-gravity effect. And if you fill the universe with such a form of energy, it actually causes the expansion of space. So the idea of inflation is that when the universe began, it had a mixture of ordinary matter and radiation, but also this self-repulsive stuff. It took over the universe, smoothed it out through causing this expansion, and then it itself decayed. So we are, in fact, the products of, not the Big Bang directly, but really most directly the stuff that came out of the decay of this self-repulsive energy. The way the inflationary theory developed historically is that Alan Guth at MIT, first of all, had the idea that if you had this kind of self-repulsive energy, it could cause the universe to smooth itself out. But once it began this process of inflation, he didn't have any mechanism to stop it. So the universe just had this runaway inflation forever. I got interested in maybe finding a way to make this self-repulsive energy to decay. We in fact found a mechanism that would permit it to decay, and so the universe could then be smooth and then end inflation.
And what period of time did this take?
So the inflation would only last around 10 to the minus 30 seconds. But in that time, it would double in size, maybe 100,000 times or more. This was a critical moment for inflationary theory, because after having smoothed the universe out with this idea, we could have destroyed it. The predictions could have been horrible for these tiny inhomogeneities that we got. But we
Because
found
you need them, or there'd be no galaxies or stars. Sure.
That's right. You need some, but you might worry that you make them too big or too violent.
Yeah.
You spoil the smoothness. But instead, we found is you got a very special pattern of inhomogeneity, of non-uniformity. It's what we need to explain the formation of galaxies.
Paul's new inflation worked because a special scalar field rolled down a potential energy hill. And when the hill steepened, inflation ended. Anti-gravity, expansion of space? Bizarre? Wait, there's more. The incredible becomes the staggering. I go to Stanford to speak with Russian-American physicist Andrei Linde, who also figured out how to end inflation. Then Andrei went further, transforming cosmic inflation into eternal chaotic inflation. I can't wait to hear his story.
Well, this history is not very short, because for a long time people were coming with similar and related ideas. Like, for example, in '79, Alexei Starobinsky came with a model which was very similar to inflationary model. But then this model was not well known in the West, and Alan Guth came with his own. What was advantage of Alan's model was its transparency and clear understanding why inflation is necessary. So this won him lots of friends. Everybody understood why you should do something like that. But he himself have said that his model did not quite work. This was amazing, and this was quite brave. It was so interesting. The idea was so great, but it did not work and did not work. I actually had an ulcer at that time. I suspect that it was maybe induced by this unhappiness of having great idea which you cannot make work. And then Alan, together with Eric Weinberg, have written a paper proving that this theory cannot be improved. But in '81, I already knew how to improve it. I realized that you can change his model quite substantially and then make it work. And then I was so excited and wake up my wife and I told her, look, I know how the universe was created. So this was quite exciting. I spent about 3 months getting permission for publication of this paper, which was a standard situation at that time in Soviet Union. And I reported this at some international conference in Moscow. And many of my friends there at the conference suggested me that give us your paper, we just smuggle it without any permission. But something stopped me from doing it, and it was Stephen Hawking. You know, after I gave a talk at this conference, next day there was a talk by Stephen, and they asked me to translate his talk. But then, in the middle of his talk, he said that this was a very interesting inflationary theory proposal, but it did not work. And I translated and explained why it didn't work. And then he said, but then recently there was an interesting suggestion by Andrei Linde how to improve it. And I happily translated. And then he said, but this proposal completely does not work for this and that reason. And for half of an hour, I translated his ideas, why my proposal doesn't work. And all people in the audience were the best people in Russia who came to hear Steve Hawking's talk. And my future depended on it. And I was translating why I am such a dumb fool. Okay. So after I translated, I told Stephen, well, I translated, but I disagree, and let me explain why. And then I explained, and then he invited me to the conference, which was the first conference on inflationary cosmology in Cambridge. And that's how new inflation started. And this was not the end of the story, because new inflation also was problematic. And in '83, I replaced it by something which I called chaotic inflation. And in '86, I found a way how to make this chaotic inflation eternal.
So define the difference between chaotic and eternal.
Well, eternal inflation is inflation which can start, but which continues all the time, indefinitely, for indefinitely large time in different parts of the universe. So chaotic inflation just says that inflation may or may not start in different parts, and in parts which it did not start, well, so too bad. But in the parts where it starts, so great, you produce enormously large volume of space, so this is a good, simple, robust mechanism of starting inflation.
And this theory of eternal chaotic inflation changed humanity's conception of the extent of reality.
Well, this is true, and now it has continued being changed because it became an essential part of string theory. I myself must say that I am extremely excited about it.
Eternal chaotic inflation defies imagination. Chaotic, bubble universes branching off, each from another. Eternal, more and more new universes never stopping. Multiple universes without number or limit popping into existence. Could reality be so ineffably vast? What about our own universe, now seeming rather puny? Its expansion, too, was hiding a spectacular surprise. I go to Lawrence Berkeley National Laboratory to meet Saul Perlmutter. Saul looked into the sky and shocked science.
Alan Guth talks about the inflationary period in the universe and has to posit that there's some way in which the universe can be forced to accelerate in its expansion faster and faster.
Exponentially.
Precisely, and perhaps with some fundamental energy that's there that's causing this to occur. We don't have any way right now of observing that in action, but we just happen to have discovered that our current universe seems to be accelerating, and probably with some energy spread throughout space that's causing that acceleration. And we don't know if it's the same thing as what was causing that early inflation, but at least it's an analogy, and at least it gives us an example of an existence proof that such things can happen. So it allows us to at least look at what kinds of physics can lead to an acceleration. They both would have a energy that's really spread through all of the vacuum. All of empty space has this energy associated with it, back then and now. And that energy can make the universe expand faster. And of course, the more space you have, the more of that energy you have, because it goes with the extra space. And so in both situations, you're usually using that same picture to describe things. They have some differences in that one of them has to turn off, because we know that we believe that the very earliest picture had a very quick exponential.
Well, the exponential seems to me a huge difference.
That's true. On the other hand, if you look at the very earliest stages of an exponential, it could look like what we see now. So in that sense, we don't know whether that's a fundamental difference between the two epochs. I'd like to step back and say that what we found in our attempts to understand cosmology has been that a amazingly simple set of principles, an amazing simple story, has ended up explaining huge amounts.
All of which are consistent with the universe having a beginning.
Exactly.
And but begin to enrich the understanding of what that beginning is.
That's right. These are all just little additions to the story. Of course, there are different ways of interpreting the Big Bang. There's also a tendency for us to hear the word Big Bang and think it means an explosion, and that's also, I think, a sort of misunderstanding of what the theory is supposed to mean. But nonetheless, the basic idea that that the universe we see around us apparently began in a much hotter, denser state, and then all distances between all points became much larger, does seem to be consistent with everything we see around us. In some sense, you may always find yourself pushing against a philosophical question, which is, okay, suppose we explain the whole thing at the very end by saying, all we need to do is to write down this one physics equation that explains how physics works, and then suddenly everything else happens. Still, you're in this business of saying, all right, but then the beginning is the physics equation, and how satisfying that feels to you is just probably personal taste.
In magnifying our vision of reality, inflation is king of the cosmos. The totality of reality, boundless, limitless, with untold numbers of universes multiplying and branching wildly. Alan Guth's spectacular realization was that the exponential expansion of space within the first billionth of a second set the universe to become as we know it today. Andrei Linde and Paul Steinhardt helped make inflation work. And then Andrei enlarged our understanding of the cosmos colossally with eternal chaotic inflation, the size of the cosmos effectively infinite. Eternal chaotic inflation is immensely disrupting. The size of all universes compared to our universe is far larger than the size of our universe compared to a single atom. As cosmic inflation reveals new worlds of unending reality, Alan and Andrei are as explorers sailing the unknown seas of space, their odyssey bringing all of us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.